Hello, so today we're going to be talking about chemistry mole conversions, the key concept in what's called stoichiometry. And we're going to do quite a few examples in this video, so if you do not have your calculator or notebook paper or anything like that handy, go ahead and grab that now, because trust me, you're going to want to use it. That way you can follow along with me in my calculations and see how I got this stuff. So the first thing we're going to talk about is conversion factors. This might be something you've already heard about in previous classes like physics or even middle school, as well as maybe in your math classes, but they're mathematical multiples that consist of two or more units that demonstrates a proportional relationship between those units. And I'll kind of show what I mean here in just a second. But in other words, I mean, the whole point is that you're able to use these to convert from one unit to another. So typically what you'll see conversion factors in are in an equation form, but you can manipulate them in other forms too. So in an equation form, we know that 1 mole is equivalent to 6.02 times 10 to the 23rd atoms or molecules. It just depends on what we're talking about. So you can write the conversion forms in a way that you can use them mathematically like this. So it's 6.02 times 10 to the 23rd atoms, and the division line means per 1 mole. And the same thing, 6.02 times 10 to the 23rd molecules per 1 mole. Okay, so if I was to use this, so converting from 6 moles of sodium to atoms of sodium that I have, I would plug the conversion factor into where the whole point is that I know that when I multiply these two units, since they're the exact same, one's on top, one's on bottom, they're going to mathematically cancel out, which leaves me with atoms of sodium. And that's what I'm wanting. Okay, so I converted completely from moles to atoms. Okay, and again, that's where they cancel out. Now, if I want to do molecules, for example, this diatomic molecule of hydrogen, we know that it's in nature diatomic. And I know back in the bonding unit, I told you that it was important to know those Brinkelhoff diatomic molecules, and this is where it counts, because H2 is technically a molecule. Now, if I was going to calculate the atoms of hydrogen total, what I have to do is that I have to convert from the moles that I'm given to the molecules of hydrogen within that mole, but then I have to ask myself how many hydrogens are per 1 molecule of H2. Well, there's 2 atoms, so you have moles that are going to cancel out, your molecules are going to cancel out, and you'll be left with atoms of hydrogen total, and that's what you should get. So again, that's how that cancels out. And again, to double check your work, you want to ask yourself, what units do I want to end up with? What is the problem asking? Well, in this example, I'm wanting to try to end up with atoms of hydrogen, and if I cancel stuff out, then that's what I'm left with. Okay, another example, something you're aware of, 1 year is equivalent to 365.25 days. The reason why it's 0.25 is because every 4 years you get a leap year. Okay, you get that extra day. So 25 cents times 4 is $1, you know, for example like that. Another way you can write it is 365.25 days per 1 year. Okay, so if I had 745 days and I wanted to convert it to years, you can actually flip this. You can flip conversion factors to fit the problem that you're doing. So I can go ahead and put days on the bottom and years on top is the exact same proportionality. It just means that I'm going to get years in the end. Okay, so that's how those cancel out and you're left with years. And then 12 inches and 1 foot. Something you're very familiar with. You put 1 foot on top, 12 inches on bottom, and if you need to, you can flip it. But in this case, I'm given inches and I want to go to feet, so I multiply, and then I'm going to 35.23 times 1 divided by 12, and you should get 2.94 feet. Okay, so the whole thing is that when you're doing this, you can treat this as 6 over 1 up here. So you go 6 times 6.02 times 10 to the 23rd times 2 divided by everything on the bottom. So you can multiply everything on top first, then multiply everything on bottom, and then take the top divided by the bottom, and that'll be your answer. Okay, so conversion factors for moles. So moles is a very important concept in chemistry because with knowing moles, you can go between multiple different types of units and dimensions. And so the way we set this up here in a little bit is what's called the Y chart, but I'm going to illustrate what the conversion factors are. So at standard conditions, STP, of 0 degrees Celsius and 1 atm as defined by Avogadro's law, 1 mole of a substance is equivalent to what we know Avogadro's number, 6.02 times 10 to the 23rd atoms or molecules, depends on what type of substance you're dealing with. So again, that's called Avogadro's number. And then it can be written as 6.02 times 10 to the 23rd atoms per 1 mole or 6.02 times 10 to the 23rd molecules per mole. But also the 1 mole of a substance is equivalent to equivalent of the molar mass of an element or a compound. And that's, again, the molar mass conversion. We know that it's related to the gram atomic weight of the atom or molecule in question. Okay, so carbon has approximately atomic mass of 12 AMU, which therefore carbon is said to have a molar mass of 12 grams per mole. So there's 12 grams of carbon for every 1 mole of carbon. This grams per mole includes 2 units. So therefore it's a conversion factor between moles and mass. And then another one that's kind of out of it is one that Avogadro determined too, and this is when he was relating the equal amounts of gases to the equal amounts of molecules. He notes that for every 22.4 liters of an element or a compound that was in the air, there would be 1 mole of that particular substance. Okay, so for every 22.4 liters of an element or compound, there's 1 mole of that substance. So we set this up into a Y chart. Now, I want to say this right now. You have to be able to memorize this Y chart. Okay, you cannot refer to it all the time. You have to be able to tell yourself, I'm using this number and I'm going to either multiply or divide. So I'm going to set this chart up to where you can write it down and illustrate it. That way you can start planning how you do stuff. And as you're doing mole conversion problems, use this chart to start mapping out your calculations before you actually do them. Okay, so what we do is we put this setup, we're going to put moles in the middle, okay, and I'm going to put volume on the left-hand side, and I'm going to put, which will be in liters, okay, and I'm going to put mass on the right-hand side, which will be in grams. So what I tell myself is that I know the conversion factor between moles and volume has to include the units of volume and moles, which we know from the previous slide is the 22.4 liters per every 1 mole. If I'm going from moles to volume, I'm going to take whatever I'm given in the problem and multiply it by this to get liters. So if I'm given moles, I have to multiply it by this, where 22.4 is on top, to get volume. That's how the units will cancel out. If I'm given volume and I want to convert to moles, I have to divide by this, where moles will be on top and the 22.4 will be on bottom. The molar mass, the grams per mole, the formula weights, the gram atomic weights, whatever, that molar mass of that substance that you're talking about is used to convert moles to mass. So if I'm given moles and I'm going to mass, I'm going to multiply by the molar mass, where grams will be on top, moles will be on the bottom, and the moles will cancel out. If I'm given mass and I need to go to moles, I can divide. Okay, so that way grams will cancel out and then moles will be on top. Then we get down to Avogadro's number. So remember, Avogadro's number is 6.02 times 10 to the 23rd particles per moles, and this can be atoms or molecules. Okay, so Avo's number, Avogadro's number. If I'm going from moles to atoms or molecules, I'm going to multiply by Avogadro's number. If I'm given atoms or molecules, I'm going to divide to go back to moles. And again, particles is atoms or molecules. There's no particular units of this, but you want to label it atoms or molecules because you know what you're talking about. You know, atoms of hydrogen compared to the molecules of hydrogen in the previous problems. Now, when you get to more advanced mole conversion problems, which we'll go in here in just a second, you can plan it out. So, like, for example, if I would need to go from particles to mass, okay, you have to pass through moles first to get to mass. So I was given particles to go to mass, I would have to divide by Avogadro's number to get moles first, and then I would have to multiply by the molar mass of the substance to get the mass. So there'd be 2 conversions you would have to do. And these arrows are very important because I use it on what I call to map out calculations. A lot of people just start doing calculations willy-nilly, they start plugging numbers in, but the best way to do it in science is to map out, to rearrange the equation the way you want to first, and then plug in what you know and then just do the math really easily. It makes the math so much easier and it makes more conceptual sense, and I'll demonstrate this more in class as need be. So let's dive into a couple problems. Let's see if I was given how many molecules are in a volume of 48 liters of nitrogen dioxide at standard conditions, STP. Okay, so the first step, you got to ask yourself, what am I converting from and to? And this is why I call the mapping from. Find out where you're beginning in the units and where you want to end up in the units. Well, I know I want to go from liters to molecules, okay, because this is a molecule. Well, based off the Y chart, to go from liters to molecules, I have to pass through moles first. So I have to go from liters to moles, and then from moles to molecules. Okay. The second step, you have to ask yourself, how many CS or conversion factors will I need? Well, the way I do this is that these arrows are important because for every arrow that you have is equivalent to a conversion factor that you need. So depending on the amount of arrows that I have in this little map that I set up, it means I have 2 conversion factors that I need. The first conversion factor is going to need liters and moles in its units, and the second conversion factor that I'm going to need is going to need moles and molecules. So I know I need to use my liters per mole, 22.4 liters per mole for this calculation to go from liters to moles, and then I need to use Avogadro's number to go from moles to molecules. And that's because they include the units that I'm associating this with. And then you just plug it in and solve it. So I start off with my 48 liters of nitrogen dioxide, and you put that over 1. That mathematically makes sense. I'm just trying to do this for symmetry purposes. I divide. Remember, according to the Y chart, I want to divide by this number. So then these are going to cancel out, and I'm going to be left with moles, which is exactly where I want to be. And then I know that I'm going to have to multiply by Avogadro's number to go from moles to molecules. And when I multiply, the moles are going to cancel out, and I'm going to be left with molecules of nitrogen dioxide. Is that what I want to be left with? Well, the problem's asking how many molecules. So if your units cancel out the way they should, then it should be good. And what I did here is that I multiplied everything on top, got the top number, and I multiplied by everything on the bottom, and I got the bottom number. Now, the bottom number doesn't have any units, and that's because the units on the bottom get canceled out by the units on top. But I'm left with the units on top of molecules, so that's where you should be. So, we'll do another one. How many liters of carbon dioxide gas is occupied by 20 grams of carbon dioxide at STP? Okay, so it's asking, based on a mass of carbon dioxide, how much volume does that take up? So, you got to map it out, okay? Map it out. I know based off my Y chart, to go from mass to volume, I have to pass through moles first. So I have to go from grams to moles, moles to liters. Based on that, I need 2 conversion factors. Okay? And that's because I have 2 arrows here. So I need 1 conversion factor that deals with both grams and moles, and then I need another conversion factor that deals with both moles and liters. Okay? So I'm going to need the molar mass because it's in units of grams per mole, and I'm going to need that liters conversion factor because it's in units of liters per mole. So I have to calculate the molar mass of CO2, which I did in a previous video, which is around about 44.01 grams per mole. Okay, so what I did was I took the gram atomic weight of each element, times them by their subscripts, added them up together, and I get around 44 grams per mole. Then I get 1 mole of CO2 is equivalent to 22.4 liters of CO2, and that's based off the conversion factor that we talked about previously as well. So I just plug them in. So I know that the first conversion factor for that first arrow is going to have to go first. If you switch them up, the units are not going to cancel the way they want to. Okay, so set it up just like you put here. So I start off with my 20 grams of CO2 that's given in the problem. Then I divide by the molar mass because I'm going from mass to moles. And so it leaves me moles on top after the units cancel out. Well, then I want to go from moles to liters. Well, I have to multiply by the liters conversion factor, and now I'm left with liters on top. And liters is where I want to be because that's what's asked in the problem. All right. How many moles of glucose, C6H12O6, are in 242 grams at STP? Well, the thing is, this is a nice one. So we're only going from grams to moles. So based off your conversion chart, you only have to do 1 conversion. So therefore, 1 arrow means 1 conversion factor. And you just need the molar mass. Now, it's a bigger molecule, so that means you have to do a little bit more math to solve the molar mass of glucose, for how many grams of glucose are in 1 mole of glucose. So what you have to do is you have to take each carbon, each hydrogen, each oxygen based off their subscripts and multiply by their gram atomic weight on the periodic table. So 12 times 6 is 72, 1 times 12 is 12, 16 times 6 is 96. Okay, I know I didn't do the decimals in this one, that's just for the reasons that I have, but when you do the problems, you need to include the 2 decimal places. Okay, so just be aware of that. I'm just doing this for condensed sake, but you're going to want to use decimal places. So you should get around about 180 grams per mole. For every 1 mole of glucose, you have 180 grams. So then you just use the molar mass as the conversion factor. I have 242 grams of glucose. I know this is kind of a pain to write out, but trust me, it's going to help you in the meantime. And then you're going to divide by the molar mass according to the Y conversion chart. You'll be left with moles on top. Moles is what we want to end up with according to the problem, so that should be the correct answer. That should be over here. So, sorry about that. How many grams of iron are in 12.2 moles of iron? Well, first, what are we converting from and to? We have to ask ourselves that. We're converting from moles to grams. Okay. So since we're given moles, we're going just to grams. We only have to use one conversion factor. And the molar mass is what's used because it includes the grams of iron for every 1 mole of iron. Okay, so there's 56 grams of iron for every 1 mole of iron, and that's based off the gram atomic weight on the periodic table. So you just plug in and solve it. 12.2 moles of iron, okay, is what you're given in the problem. You have to multiply by the molar mass to get grams on top. The moles are going to cancel out, and then you get 56 times 12.2 divided by 1, which is the same thing as itself. You should get 683.2 grams of iron. Excuse me. So how many atoms are present in 3.2 moles of elemental calcium at STP? So we're going from moles to atoms. We're given moles, which means we can go straight to atoms. But what number do we use? We use Avogadro's number. Woohoo! So we're going to use Avogadro's number as a conversion factor. So we're given the 3.2 moles of calcium, and then we're going to multiply by Avogadro's number according to the Y chart, which means we're going to have 6.02 times 10 to the 23rd on top. And then the moles are going to cancel out, so it'll be 3.2 times 6.02 times 10 to the 23rd divided by 1, which is itself. And you should get 1.93 times 10 to the 24th atoms of calcium. Okay, and again, this is just showing the canceling out, double check your work. Atoms, is that what I want to end up with? That's what was asked in the problem. There you go. All right, so hopefully a lot of this practice helped out. If you have any further questions, especially in regards to the definitions of gram atomic weight, formula mass, molar mass, they're all very similar. And I completely understand if you're confused there. But please come talk to me. That way you can have those clarifying questions answered. But really don't overcomplicate it more than you probably are. Just really simplistically, just reading the information on the periodic table, manipulating it the way you need to mathematically, plugging in and solving it. It's not that bad. The biggest thing is the units. So always double check what units you start off with and what you want to end up with. And if you map it out correctly, then the math shouldn't really matter. You know, the math should just be able to plug it in, use your calculator, and you should be good. Okay? But if you have any questions, please come talk to me, email me, whatever you need to do. Otherwise, thanks for watching this video, and I'll see you in the next one, and see you in class. Bye.